graph, and for each arc, there is at least two numbers. Normally, it's actually three numbers. The first one is the cost, then the upper bound, and then the lower bound, optionally. And for each vertex, there's a number that is a demand. So you have a graph of like a weighted graph like that. And what you're asked about in the minimal cost network flow is to minimize. So you have let's say that let's define the v plus of I and the v minus of I. This is a minus for each I, the vertex of the graph. The v plus of I is the set of nodes to which you can get from I. So like you have an arc that goes through, so it's the set of k, the vertices k, such that there is an arc that goes from I to k. And v minus of I is the set of k, the vertices k, such that there is an arc that goes from k to I. So from vi you can come into I, and into v plus you can get from I. These are the vertices. Okay. So node I. There are some nodes that form v minus of I, and there are some nodes that form v plus of I. There might be some nodes that are both in here and here, but the important thing is that you can get from I into this subgraph, and you can get from this subgraph this subset of nodes into I. Okay, and we are minimizing. So we to each arc there is an assigned variable xij. So ij is an arc from I to j, and xij can be interpreted as the flow that is flowing through an arc, right? We are minimizing the summation over all arcs, the cost of a unit of flow through an arc times the size of the flow, the amount. Is this clear? Okay. Then we need to make sure that the flow is continuous and not interrupted anywhere. So the sum, it's called the balance equation. The sum of all of the flow that flows into I minus the sum of the flow that outgoes from I must be equal to the total demand that we are having. Cool. So this is overall framework of minimal cost network flow. Then, so it's a simple problem. It's a totally unimodular problem, which means that it's it can be solved with linear relaxation. And then there was an example, and now we are going to give a few like special cases, important special cases of this minimal cost network flow. Okay, so the first example is the transportation problem. In the transportation problem, there are no transshipment nodes, meaning that a transshipment node would be a node with a demand equal to 0. So there in transportation, there are no nodes with a demand equal to 0. Transportation problem is based on a bar-heighted graph, meaning that the set of all nodes can be split into two parts. The first part and then the second part. The important feature of this division is that there are no arcs that are going from a node, like between two nodes in the same path. So arcs like this are prohibited. There are no arcs. And the arcs can only go from one part to another one, and they are normally just directed like just one way. Not they are not edges that go both ways. So the question here is basically, given that you have a supply, for example, in like some supply in the cities, and you have some demand somewhere, I don't know, in other countries, you need to decide through which routes you need to you need to like distribute your supplies into the overseas countries. So this is the motivation for the specific formulation. Therefore, this problem is called transportation problem. We only need to specify the cost on the arc because supposedly the capacity is assumed to be infinite, and we don't have a lower bound are all equal to 0. So we don't have to worry about these two numbers, upper bound and lower bound. We only need to worry about the cost and also the demand. That cannot be equal to 0. Okay. Are there any questions about this calculation? Yeah. Let's take a look at the example. We are transporting goods from supply cities to demand cities. We are given a number. We are given a number of like we have 3 supply cities and 4 demand cities, and in each of the supply cities we have certain amount of supply, and in each of the demand cities we have a certain amount of demand that is put right here. Obviously, the total amount of supply must be equal to the total amount of demand. Otherwise, the problem can be solved. We also are given a cost of unit of flow that flows through an arc. For example, from Cleveland to Boston, the cost of shipment of like a particular unit of goods is $35. So like we end up with a matrix that defines for each pair of a source city and a target city, you have a certain number that specifies the cost Cij. How do we you can take a look at the specific network, how it might look like, and its formulation is the following: the mathematical formulation that you would need to come up with here. If S are the supply nodes and D are the demand nodes, we are having 2 different sets of constraints that basically specify which constraints we are trying to satisfy. Like if we are worried about the flow that is outgoing from the node, or we are worried about the flow that is incoming into the node. The total cost is the sum of the products between Cijs and Xijs, and we don't have any particular constraints on this problem. We do not put anything over here, but generally speaking, if all of the constraints, all of the coefficients in the problem B and C are all in integer numbers, which is normally the case, you can just solve this optimization problem over real numbers, and you will obtain an integral vector as a solution to it. It's obvious how to reconstruct the optimal flows, the optimal scheduling from the solution problem, right? Cool. So there's the shortest path problem, and I would like to give you an example of a non-trivial, like not obvious formulation of a practical problem as a shortest path problem. So just a reminder of what is a shortest path. In the shortest path formulation, it's still a minimal cost network flow, so it still has this kind of structure with a single number assigned to a vertex and 3 numbers assigned to an arc, but it has a different structure compared to the transportation problem. In the shortest path, we have two nodes that are special: the source and target. Source and the target. And in the source, the demand is -1, and in the target, the demand is +1. And between these two nodes, there's some certain network of like it could be directed, it could be not like normally it's an like acyclic graph, but it could be also it also could have a cycle. So all nodes are transshipment. Like in all of the nodes, in all the other nodes that are between the source and the target, the demand is all equal to 0. So, for all our nodes, the demand is equal to 0. All edges have a lower bound of 0 and an upper bound of +infinity. We don't really care about the upper bounds because we only have a unit of like 1 unit of flow anyway. So it's there will not be any more flow that we actually need to carry. We want to send 1 unit of flow from S to T using less expensive paths. So we would like to find the shortest path between the two nodes. The applications in logistics are obvious. However, here's a problem about building a house. Actually, like any kind of construction job can be formulated like this, and a lot of interesting scheduling problems as well. The table below lists the critical activities and predecessor activities, which are the activities that must be completed before this activity takes place. We are interested in the target term, like the minimal term in which we can construct a house. You can see that there's like on the left hand side there are activities listed by code, and on the right hand side there are predecessors. It's actually more interesting to look at the predecessors because the arcs, like when we are going to be like, this is a shortest path problem. It's a statement. Like it can be modeled as a shortest path problem. It's not obvious right away, but if you think about the duration of construction for each activity as the cost that you have to pay for, like it's the cost that you have to pay, then probably you would like to maximize this cost, or you would. So let's go this way. If you're having two nodes, which are the source and the target, the source node is the node that corresponds to the very beginning of construction, and the target node is the node that corresponds to the completeness of construction. And between these nodes, we will have nodes that correspond to each task. So first of all, we would like to define the nodes. The arcs between the nodes would be the terms of completion. So an arc from the start node into any node in the graph from which we can start. For example, here I think there's only one starting node that is feasible, which is the activity A. Activity A is the only node that has no predecessors. So from the start node, we will have a cost of 0 because we just start right away. But for any other node, there will be a cost that we will need to pay before we can start the next activity. And the question that we are really asking here is, what's the longest path that we would need to take, since we will take all of the paths. Like we will, in order to construct a house, you need to go through all of the nodes. But some of the nodes can be processed simultaneously. So what you are really interested in is a continuous path from S to T that is of the largest length. Or if you reformulate it, you can say that it's the shortest path if you are taking durations to be negative. Any questions regarding the high level idea? Guys, I feel like you're lost. Are you? Like if this is the case, then I can just repeat everything.
I understand the problem, but like the solution.
Mm-hmm.
You know,
So it's still not clear, right? But do you agree with me that okay, so let's start with the beginning, that with the definition of the nodes. Do you understand how I defined them? Okay, so the arcs in this problem are going to be like going from the predecessor activity, that is listed here, to the actual activity that is listed on the left hand side. Okay, so and the weight that I'm assigned to each arc is a negation of the duration. Now this is the graph that we will get if we process the table above. This is the origin node, which is node S on the left hand side. This is the destination node. And what I'm saying is that as we constructing, like imagine yourself constructing a house, you have completed the task A. Now you can start completing task B. So while you were completing task A, you were following this edge right here, this arc. Now you can start completing task B, and when you're completing task B, you're essentially taking both paths. So you take this path right here. Let me take a. You're taking this path right here, and you're taking this path right here at the same time, simultaneously, because as you like when you have completed task B, you can start task E and task C simultaneously, and you can imagine that it's like, I know, it's like this edges, these arcs are threads, and you're firing up one end of the thread, and then the fire spreads on threads everywhere. And you're really asked about at which point at the destination there will be the last spark, because some lines will actually converge, like get back to the destination node like earlier. Some will get there later, and you're asked like what's the last task that's going to be completed. But what's the last kind of spark that gets to the destination node? Is that still to how to like?
we're here now.
Okay, I would like to clarify so that it's like absolutely clear.
Yeah, but like when you're in node B, is but are you allowed to go like both ways?
Yes, yeah. So you're like here, you split and you go in both directions simultaneously.
But you like in a shortest path problem, you only go one route.
Yeah, that's true. So so yes, so you have imagine yourself this process of burning all of the threads at the same time. Now you are like there is the last thread that will be still firing in this process of like simultaneous burning. You can take this thread and see where exactly from what, like you can take this, like let's say that this is the thread that is burning the last. So everything else has burned out, and this is the last thread. Now you can take a look at where exactly the fire to like got to this thread, and like from where exactly was the last time that the fire like got here. It's probably not a very clear let's say this. So we are saying that an edge is corresponding to a task being processed or being completed. We cannot start doing doing a task before we have completed everything. So basically, before we start completing task J, which corresponds to this arc, we need to complete all of these tasks. So we once we have got to j from node I, we will still need to wait in the node j before our clones get to j from node h and from node g, just because the tasks g and h still have not been completed.
I get it now.
Right.
Yeah.
And what we are asking here is like the last arc that is going to be completed is going to be the last action that we are doing, right? And so we are asked about like one of our clones will have to make this longest path from one end to the other. So like when we are cloning ourselves in node B, there is one clone that goes this way and then being cloned in node C, and there is one clone that goes this way and being cloned in node E, and one of these clones will eventually take the longest path from S to T, and this clone is going to be the one that is completing the entire job. Therefore, we are interested in finding the longest path from S to T. And finding the longest path from S to T is basically the same thing as finding the shortest path if you negate the cost of each arc, because this is from maximization to minimization. The negation of a minimization is the same as maximization of negation, right? Is that clear? Any questions? Because it could be that you're getting a similar question on the exam, so it should be clear for you. Okay. All right. So it's some tricks and suggestions regarding this. So normally, when looking for a formulation, it's easier to start by defining the nodes, as you just see, as you just saw that we first like here we first defined nodes that correspond to tasks, and then we proceeded to formulate the arcs themselves. Many times it's useful to define artificial starting and ending nodes, and it's useful to give explanation what exactly a unit of flow means. So this comments actually refer more to the example that we have gone over during the lecture. If you would like, I can stop on this and give you another example that we have discussed during the lecture that is not in the book, or you can watch it on YouTube. But since you're here already, I can go back and reiterate that example. It's an example about the general case minimal cost network flow, and quite an interesting one. Okay, so it's up to you.
I don't think it's necessary for me at least.
Okay.
Okay.
Okay, sounds good. Yeah, so duplicating the nodes might help. Again, that refers to the other example, but make sure that you at least take a look at that example during the lecture, because it's the only example that we have gone over with the minimal cost, with the general as a general example of minimal cost network flow, and it's important to understand how to formulate those, because they are actually extremely common in applications. Okay, so we have another exercise, but I would probably instead of going this direction, I'll probably come back to the lectures and try to speak a little bit about the one topic that we did not cover regarding submodularity. So we have this scheme about the problems which are easy from the computational viewpoint. How do we know that they are easy? Just because we have polynomial time algorithm to solve them, and these algorithms, these polynomial time algorithms, normally come from methods to bound the methods to construct bounds on the solution. You remember that We had a method to construct bounds on to construct dual bounds. We had methods to construct primal bounds. So we during the lecture last week, we have taken a look about like on the methods to construct dual bounds, particularly the LP relaxations. Now I would like also to speak about the methods to construct primal bounds and which problems can be solved exactly using this heuristics that allow us to construct the primal bounds. Do you guys remember anything about heuristics? I was okay. Heuristic aims to find the like a good feasible solution, generally speaking, and there is a class of problems that like for which a heuristic of a greedy heuristic results in the optimal solution, in fact. So that doesn't give you just any feasible solution. It's actually guaranteed to give you a feasible solution that is optimal. It's based on a formulation where it uses a notion of submodularity. So a function, a set function from subsets, subsets into our real numbers is the following has the following property, that for any two sets, for any two subsets of the set of n numbers, f of a, f of one subset plus f of b is greater than or equal than f the value of the function of a intersection with b plus the f of a union with b. There's an equivalent definition for this, is that for any two sets A and B, for any two sets A and B that are included into one another, you're having set A. Okay, so you're having a set B and you're having a set A, and they are included into one another. And you have a J, a separate point, J, a separate number, since we are talking about the sets of numbers. You have a separate like value of J, and then you're trying to include this value J into set A, and then you're trying to include this point J into the set B, and you're taking a look at how much the function f is being marginally increased during this event of inclusion. And you like the property that function f must satisfy is that like for the smaller set, inclusion of a new number must be more significant than for the larger set. So like once you like if you were to join J with A, that would give a greater increase for the function f as a result than if you were to join J with the set B. So this is a definition. An example of this is for a concave function phi. Just a reminder what the concave function is. Function of this. For a concave function phi, f of x can be defined as a phi of the size of the set. Right. It's let's say that we like our set is since we are talking about about natural numbers. Let's say that our set is like this 5 numbers. And if we would like to understand what is the value of f on this subset of five numbers, we would just need to take the value of 5 of this function 5. And any such concave function 5 defines a function f according to this rule. And this f turns out to be submodular. So you can think about this like intuitively. Submodular function means that means the diminishing returns. You probably have heard about diminishing returns before, have you? Okay, so it's basically the same thing. You're getting something new into your possession, and if you already have a lot, this like bringing in something new doesn't matter too much. But if you don't have too much, then it's like bringing in something new is like actually might actually make a difference. From this perspective, a submodular function behaves more like concave function, but from the perspective of optimization, it's actually more similar to a convex function. A submodular integer optimization problem is the problem of this form right here. So we again have a linear objective, and we have a set of constraints for each. Like we have 2 to the n constraints, which are defined with the function f, which is the so basically this entire problem has 2 main components, or 2 main parameters. It's the vector c and also the function f. There are 2 to the n constraints in this problem, which can be put as follows: for any subset S of n coefficients, the sum of xj, where j belong to the subset of indices, is less than or equal than is bounded from above by the value of the function f of s. There's a whole lot of different examples of problems like this, and it's a quite general idea. The statement that is interesting about this submodular integer problem optimization is that the greedy heuristic that follows like this in fact results in the exact solution to this problem, given that the function f is a submodular function. So we can formulate a huge class of problems, like a huge class of problems that are polynomially times solvable, because this greedy heuristic is in fact very easy to implement, even though they are extremely complex. They contain exponential number of constraints, and generally it could be extremely hard to solve. So let's take a look at this greedy heuristic. Any questions so far? Any questions regarding the problem? Or let's take a look at this greedy heuristic. In this greedy heuristic, we are ordering the coefficients c, or we are reordering in fact the variables, so that the coefficients are going from the largest to the smallest. And there is coefficient cr. So after the rth variable, the other variables are corresponding to negative coefficients. So like we would like to fix that r to understand where that lies. Then we set xi for any I. We set xi to be equal to f of subset from 1 to I minus f of subset from 1 to I minus 1. as like we are setting xi to be like this if I is less than or equal than r, and xi is going to be equal to 0 if essentially the corresponding coefficient c is less than 0. So if you probably remember that we had like a similar idea of a greedy heuristic where we had also ordering, and we were also like ordering variables with respect to its value. It's like marginal value, because our like value or the marginal value was something like di over ai in case in case that we had like maximization of cx subject to ax less than or equal to b, and then we were looking at ci over ai in order to understand. So this was the vi, the value of a particular item, and we were thinking about putting an item into our box if this relationship, like if this relation was big or not. So this idea is a straight generalization of this idea. The only caveat here is that we don't have the AIs anymore, and this again, if we like, there is a way to just put the put this problem with AIs could be put in this form, and then F would have a specific structure. So basically, these are the same. In fact, like this problem is a sub problem of the general form. Another important assumption that would allow us to solve this problem is that a function f is in fact non-decreasing. So besides submodularity, there is a requirement of non-decreasing. Once again, if you have any two subsets A and B, and A is subset of B, you must require that the value of f of the smaller subset is like not greater than the value of f of the larger subset. But that's a pretty straightforward and easy assumption. And there's a theorem that says that the submodular integer optimization with submodular non-decreasing in an integer valued f is solvable with the greedy heuristic that we have just described. And let me give you an example with the minimum spanning tree. We are planning to set up a telecommunication network, and we are trying to make it so that like the cost of a line between I and between the two vertices I and j is minus Cij. How we can create a connected network optimally. So what we are doing here is we are finding a maximum weight subgraph that is a tree. This is called the maximum spanning tree problem. Is the formulation clear? Are there any questions? So we are maximizing the sum of edges the sum of cost of, or the sum of value of the edges that is going to belong to a graph where x is this indicator if an edge belongs to our subtree or not, subject to the constraint that the subgraph needs to be a tree. Basically just making sure that there's enough like arcs that we are considering would be sufficient. Okay, so an example so an example of application of the greedy algorithm is the following. We are ordering edges in this order. So we are basically, you can see that this problem here is a special case of this problem. So we can order the edges with respect to the costs C from the largest to the smallest, and then go along the line of edges in this direction and see if we are adding our edge into the subnetwork or not. So for example, this this edge, so like the first four edges we would take into our subtree, but the fifth edge would not get in because it would form a cycle. So you can take a look that we have the first edge is 3, 4, then 1, 5, then 1, 3, and then 3, 6. So it's 3, 4, 1, 5, 1, 3, and 3, 6. 1, 3, and 3, 6. And if we were to add another edge, which is 5, 6, we would create a cycle from like 1, 5, 6, and 3, and therefore this would contradict our goal of creating a tree subgraph. Therefore, we are not taking it into our subtree. And if you continue doing the same way all the way to the last edge, first of all, you will do the entire calculation, but then like an amount of time that is proportional to the number of edges, and you will end up with the optimal solution, the maximum spanning tree problem. This is one example that I wanted to cover here right now. Of course, everything that I'm speaking about submodularity needs to be proven, because I didn't give proofs here. We'll see if we have time during the lectures for that, and then I'll probably expand on this example a little bit more. I just wanted you to know that we have covered easy problems that are solvable with algorithms that are based on dual bounds. We have seen easy problems that are solvable with the dynamic programming yesterday, and now we have seen easy problems that are solvable with algorithms that are constructing primal bounds. So all of these algorithms can in fact solve problems that are easy, and like from now on, like after the exam, most probably we'll come back, we'll shift towards hard problems and see what we can do if none of this heuristical solutions can work. Sounds good. Thank you. If you have any questions, I'll ask you around for 10 minutes.
Will we be posting any midterms for previous years?
So I'm planning to. It could be that I'll do that. Yes. I will see if I have time for preparing that. Yeah.